So this is the 36th video on rigid body kinematics. Okay, this is in continuation of the 35th video. Okay, but before going ahead, I would like to state two things. First, that if you carefully go through videos of this channel, it's complete. Okay, you don't have to refer to any other book. You don't have to go anywhere else. Okay, if you go understand this fully, then you understand the theory and numerical of this properly. Then you take up any problem from any source, and I'll be sure you will be able to solve most of them. And in case you have any doubt, you can refer to the comment box. I'll answer it. Okay. And one more thing, that all the videos of this rigid body kinematics have been put in the playlist. Okay. So there you can go and see whichever video you want to see. Okay. Fine. So now we are continuing. This is the continuation of the instantaneous center of rotation. Okay. So now we are discussing IC, instantaneous center of rotation. All right. Now see, one thing I would like to say, that we discussed that suppose F is a reference frame and M is some rigid body which is in plane motion with respect to F. Then it was proved in previous two videos that definitely M possesses an IC with respect to F. So let this be the instantaneous center of rotation of M with respect to F at certain instant t. Then line through IC and normal to the plane of rotation is called the instantaneous axis of rotation. Alright. So what is meant by instantaneous axis of rotation? Instantaneous axis of rotation is written in short as IA. I for instantaneous, A for axis. This is called the instantaneous axis of rotation. Instantaneous axis of rotation. Instantaneous axis of rotation. And what is meant by this? A line through IC and normal to the plane of rotation. That is the instantaneous axis of rotation. Through IC and perpendicular to the plane of rotation. That is called the instantaneous axis of rotation, which is in short mentioned as IA. Okay, so this is the instantaneous axis of rotation. Alright, so line through IC and normal to the plane of rotation is called the instantaneous axis of rotation. Okay. So one more thing I would like to say. Suppose M undergoes plane motion with respect to F. Okay. Then M definitely possesses an IC, as was proved in the previous videos. Now question is, how many ICs does M possess with respect to F? Answer is infinite. One in every base plane. Okay. So if M undergoes plane motion with respect to F, then M possesses infinite number of IC, one in every base plane. In every base plane, and the base plane may be real or imaginary. Either it may contain some of the material points, or it may be an imaginary extension. Okay, hypothetical massless extension of the body M. One in every base plane. Okay, one in every base plane. The base plane may be real or imaginary. This point should be kept in mind. For example, just demonstrate this point. See, the point is this. This is the reference frame F. This is the body M in plane motion with respect to F. This is the plane of rotation of m. Suppose omega is the angular velocity of m with respect to f. Suppose anti-clockwise sense. This is the base plane. These are the base planes. See, it's a property of plane motion that all the real and imaginary locations of m on any line through on a straight line normal to base plane have the same velocity. Is it clear what I'm saying? I'm saying that if m undergoes plane motion with respect to f, okay, then all the real and imaginary locations of m on a line straight line normal to the base plane will have the same velocity. For example, just suppose instead to understand this concept, suppose G is the ground frame, okay, and M is a rigid body. Suppose that this is the circular side view of a circular drum. C is the center, R is the radius. This moving at a speed v, rotating omega. Suppose it undergoes pure rolling over this surface. This is the body M. It's a circular drum which is undergoing plane motion with respect to ground frame G. Center moves at a speed v. So these are the base planes in which the material points of the drum move. Okay. Now I take any line which passes through center and normal to the plane of rotation. For example, this line through center C and normal to plane of rotation, this line. So all lines on this, all the real and imaginary locations of M on this line will have the same velocity v. Suppose it's undergoing pure rolling here. We know from theory of rigid body kinematics, previous videos, that the highest point will have a speed of 2v. That all the locations of M on a line through this point will have the same velocity 2v. Okay, so it automatically follows that suppose we'll see just now that IC of this body will be somewhere here in this base plane. Here we have assumed that it is undergoing pure rolling. I will just now prove that IC will lie here. Okay, then all lines on passing through this IC and normal to plane of rotation will have the zero velocity. So by definition, all the locations of real and imaginary locations of M on a line through this point and normal to plane of rotation will have zero velocity. By definition, each of these locations is IC of M with respect to F. Okay, so this point has to be kept in mind, that if M undergoes plane motion with respect to F, then there are infinite number of ICs of M, one in every base plane. And a line through instantaneous center of rotation and normal to plane of rotation is called the instantaneous axis of rotation, or in short it is written as IA. Okay, that is called the instantaneous axis of rotation, or IA. Alright, so this point should be kept in mind. So what is the instantaneous axis I have told, and how many ICs are there, that also I have discussed. Infinitely many ICs, one in every base plane. Okay, ICs may be real or imaginary depending on whether the base plane is real or imaginary. Okay, fine. Alright, so these are a bit. Okay, so now we'll discuss some problems. So methods to locate IC. There are various methods. Locate IC. First method is by observation. Second, by using IC concept. Third is by drawing lines. Fourth is this. Let's write another one. By concept of omega cross Vp naught by omega square concept. Fourth is by drawing lines. Fifth is by combination of various methods. By combination of what? Various methods. Alright, fine. So this I have it here. So first method I take up. So before going ahead, one thing I'd like to state the result of previous video. That is, if this is the frame F, this is the rigid body M in plane motion with respect to F. This is one of its IC in one base plane. Okay. This is some other point P. Okay. P and IC are in the same base plane. This is the vector R from IC to P. Suppose angular velocity of M with respect to F is omega clockwise. So velocity of P with respect to F will be omega R, where R is what? The magnitude of vector R. R is the magnitude of vector R. And VPF will be normal to this line corresponding to sense of omega. So in this case, omega is clockwise. So this is IC. The velocity of P will be omega R like this at right angles. So distance of P from IC is R, where omega R is the speed of point P. So VPF equal to omega R, and direction of VPF is normal to this line corresponding to sense of omega. For example, see, if this is F, this is M. Suppose sense of rotation of M with respect to F is omega anti-clockwise. This is IC, this is P, this is R. In this case, VPF will be omega R, normal to this line in this direction, like this. Okay, and value of VPF will be how much? Omega R. So this is the IC concept. Okay, fine. Now I love this one, alright. So I take the first method by observation method. Okay. So this is a circular view of a side view of a circular drum. Side view of circular drum it is. C is the center, R is the radius. Center moves at a speed v rightward with respect to ground. It undergoes pure rolling. Omega is clockwise. Since this is the fixed ground surface. This is the ground surface. Here it undergoes pure rolling. It undergoes pure rolling here. So since center is moving rightward and this undergoes pure rolling over the ground surface, the sense of omega should be clockwise. Okay. Now we have to tell this is the body M, drum is body M. Instead of F we have ground frame G. Alright, fine. Now we have to locate the IC of this drum with respect to ground at this instant. Now in this case IC of drum with respect to ground will be this location. This will be the IC. Why? This follows from the pure rolling concept. See, assume this is the ground surface. This is fixed with respect to ground. So from ground, see, D is the material point of the drum in contact with material point G1 of ground, and D1 is the material point of drum in contact with G1, location of ground frame. G1 is the location of ground frame, D1 is the location of drum. Both are in contact at the given instant. Okay, fine. Now, as seen from ground, G1 is at rest. The drum undergoes pure rolling over the ground surface. From pure rolling criteria, it follows that velocity of D1 is same as velocity of G1. Since velocity of G1 is 0 with respect to ground, so velocity of D1 with respect to ground is also 0 from pure rolling concept. So velocity of D1, material point D1 of the drum with respect to ground is 0. So by definition, D1 is the IC of drum. D1 is the IC of drum with respect to ground. So this is the IC of drum with respect to ground. So this has been obtained by direct observation. Alright. I got this one. So now, recall we discussed this. For example, suppose D2 is the highest point of drum. D3 is the highest point of drum. This point of drum at the same level as center and lying on its circumference. D4 is the point of drum on its circumference. D4. Suppose this angle is theta. Now you recall in the chapter on rigid body kinematics of the second chapter, we found the relation between V, omega and R using the SRC procedure for velocity. So same relation can be obtained using IC concept. See, we have to find the relation between V, omega and R. So center C is at a distance of R1 from R from IC D1. D1 is IC and center C is at a distance of R from IC. So from the IC concept it follows the velocity of C is simply omega R. But velocity of C is given to be how much? V. So V is equal to omega R. Alright. V is equal to how much? Omega R. Same relation we have obtained again. Is it clear? So V is equal to how much? Omega R. So this relation which we obtained by SRC method, that has also been obtained directly. Okay. Now I would also like to know what is the velocity of D2 with respect to ground. Now what is the distance of D2 from IC D1? D1 is the IC, D2 is the highest point, diametrically opposite point. Distance between D1 and D2 will be R plus R, 2R. The velocity of D2 will be equal to IC concept, from IC concept, omega into 2R. That is 2 omega R. But omega R is how much? V. So this becomes how much? 2V. This also we obtained in the second chapter on rigid body kinematics. In the previous videos you will go and you will get it there. Okay. Now what about velocity of D3? One more thing, just I'd like to say that see, this is C, this is D1, this is D2. Velocity of C is V. V is no direction of V will be normal to this line corresponding to sense of omega. So VC will be like this. This is just V. V is right angle to this direction. Velocity of D2 is how much? 2V. There is also right angles to this line. Line joining IC D1 and D2 is 2V in this direction. Okay. Now I'd like to know the velocity of D3 using IC concept. IC concept is this. This is point D3. This is the IC D1. D1 is the IC. So this is R, this is R. I join this. This is omega. By geometry, R right angle. This right angle triangle by Pythagoras theorem. This distance is R root 2. So velocity of D3 is how much? R root 2 into omega. So that becomes root 2 omega R. But omega is how much? V. That becomes root 2V. Okay. So all these results which we obtained by SRC procedure for velocity, they have been obtained directly also. You can see it. Alright. What will be the direction of VD3? That will be normal to this line corresponding to sense of omega. So So in this direction, VD3 will be right angles to this line corresponding to sense of omega. Omega is clockwise, so VD3 will be in this direction at right angles, this one. Okay, fine. So VD3 will be how much? Root 2V at right angles, so line joining the D1 and D3. Okay, fine, alright. This are a bit, okay. Now I take D4. This is the D4, point D4. This is the center C. C is moving at a speed V. This is 60-degree angle. Theta, sorry, theta. Not 60, theta. This angle is theta. This angle is just equal to theta, alright. This is the IC D1. D1 is the IC of the drum with respect to ground, okay. Now we have to find the speed of D4 using IC concept and also the direction of its velocity. So he joins D1 to D4. D1, which is IC, is joined to line D4. Let this distance be R1. From IC concept, velocity of D4 will be R1 omega at right angles to this line. Since omega is clockwise, it will be in this direction, VD4 at right angles to this line. Now how to find this distance R1? So this we can find directly from cosine law of triangles applied to this triangle. C D1 D4 cosine law. Cosine law, you know, R1 is equal to root under R square plus R square minus 2R square cos of pi minus theta. This is theta, this is pi minus theta, cosine law. This becomes cos pi minus theta is minus cos theta, so plus 2R square cos theta. This becomes how much? 2R square 1 plus cos theta. Alright, fine. So this becomes how much? 2R square into 2 cos theta by 2. On simplification, this becomes how much? 2R cos theta by 2. Alright, this is R1. So VD4 is how much? R1 omega. So VD4 becomes omega into 2R cos theta. 2 omega R cos theta by 2. Omega R is equal to V. So this becomes how much? 2V cos of how much? Theta by 2. Okay. So same answer has been obtained again as we obtained the SRC procedure for velocity. And this is at right angles to this line. Okay. So it is something like this. I hope it is clear now. Fine. How much will this angle be? This angle will be how much? This angle will be see, this angle is how much? Theta. This is pi minus theta. These two angles when equal, isosceles triangle, radius equal. This also becomes how much? Theta by 2. So this is this becomes pi by 2 minus theta by 2. Okay, fine. See, so this is how much? See what I am saying, that by geometry VD4 will make an angle of this much, theta by 2 with the horizontal. Is it alright what I have said? Clear? See, this is theta, this is pi by 2. This angle will be how much? Pi by 2 minus theta. And this is pi by 2 minus theta by 2. Okay, fine. So you can see this is theta, this is right angle, this is pi by 2 minus theta. Okay, and pi minus theta, this is theta by 2, sorry. This will be this angle will be theta by 2. This is theta, this is pi minus theta. So this is theta by 2, theta by 2. And this is theta, this is right angle. This angle is how much? This angle is equal to pi by 2 minus theta. And this is how much? Theta by 2. These two angles add up to how much? Pi by 2 minus theta plus theta by 2. Pi by 2 minus theta by 2. This is pi by 2. So this angle becomes theta by 2. So VD4 makes an angle of theta by 2 with the right one horizontal. Again, you see same result which we obtained by SRC procedure for velocity. Same result we have obtained again here also. Alright, fine. So VD4 makes an angle of theta by 2 with the rightward horizontal. Alright, fine. The same answer we have obtained again. Alright. This was the 36th video on rigid body kinematics. Okay, so we'll continue in the coming videos. Also 2 or 3 more videos I'll take up all such problems on IC. Okay, so this I close it here. Alright, fine. Alright, fine.